Okay, so we're back. Now, instead of a mass on a spring, we're going to analyze all the different characteristics of a pendulum. So we're going to look at it at a position theta as it swings, and then returns back to that position. So in the middle, again, is our equilibrium position, just like a mass on a spring. And then here is going to be our maximum displacement, just like mass on a spring. Okay? So the 5 quantities that we're going to be analyzing, same ones: force, acceleration, potential energy, this time it's due to gravity instead of elastic potential, kinetic energy, and velocity. And we're going to look at the maximum displacement position, so maximum theta, the equilibrium position, and then theta prime, which will be someplace not at max, not at equilibrium, but someplace in between. So for example, if I pulled this out to 15 degrees maximum theta, theta prime might be, 10 degrees, okay? So not max theta. All right, here we go. The force in any pendulum that's swinging is due to gravity. And that force is actually going to be the gravitational component that's tangent to the circle. Now we know gravity acts straight downsies, so mg, straight down. But we're going to have to draw another triangle. This will be the good triangle. So one of the components is in line with the string itself. Theta gets transferred down here. And the other component, the one that we care about, is this one, the one that's tangent to the circle. Okay? Since that's opposite the angle, theta, the force, the component that pulls parallel or tangent to the circle, is mg times the sine of theta. That'll give you the force. The force at equilibrium at the bottom of the swing is actually going to be 0. And the reason for that is, since if we cut the string at this point, it would fly off tangent to the circle. That means it would fly off horizontally. And although it does have lots of horizontal velocity, there is no horizontal gravity, so there's no force doing that. In fact, at the moment it gets released from the string, it would follow like a parabolic, like a projectile type path. So the force there is 0, but the velocity, if we came all the way down here, is going to be maximum, and we'll figure that out in a couple of minutes. To solve for the acceleration, we're going to again use Newton's second law, which is just F equals ma. And we're going to put in mg sine theta for the force, set that equal to ma, and the mass will cancel. So acceleration is just g times the sine of theta. At equilibrium, so at the bottom of the swing, again, there's no gravity pushing it horizontally, so the acceleration is also 0. Now that's the fastest spot. It's a little bit tricky because it has no acceleration but maximum velocity. Okay? The potential energy due to gravity, that's a little bit trickier. Its maximum here, it's going to be at its highest, but how do you actually calculate that? If we go back in our memory banks from our sheet problems, you'll remember that potential energy due to gravity is equal to mass times gravity times height. Now the height is, sorry, got to move the butterscotch. The height is this distance right here. It's the difference between the center of mass when it's at its maximum angle, theta, and the center of mass when it's actually at the equilibrium position. So the easiest way to represent that will be to actually draw a right triangle. So there's my right triangle. And the height is this right here. That's H. Now the full length of the string, in fact, I'm going to label it here, L. That hasn't changed. So from the pivot point to the center of mass is still L for this whole thing, okay? That's the same. I know it might look a little longer in my picture, but you're just going to trust me. So H is actually the whole length of the string minus this side of this right triangle. And if you remember your trig, the side that's adjacent to the angle is the cosine component. So H is L minus L cosine theta. That's the height that I actually lifted the pendulum vertically. So now we're going to replace H with this whole quantity. So the potential energy due to gravity is mass times gravity times L minus L cosine theta. So that's what I'm going to put here in our table. Okay. Onto the kinetic energy. We're going to get back here in a minute. Onto the kinetic energy. The kinetic energy at maximum is 0 because that's the spot where it stops. That's going to be the peak of flight on either side. And the velocity is also 0. Okay? Now let's fill in the rest of these at equilibrium. The equilibrium for potential energy spot, that's going to be 0. Again, because we're right here, and this is the bottom of the swing, so for that pendulum, now I'm not talking about if it's lifted off the ground, but for the pendulum itself, that equilibrium spot is the lowest spot the pendulum will ever be. That's where the potential energy is equal to 0. The kinetic energy is 1/2 mv squared. And of course, to figure out the velocity, now we're going to use these two together. So here's how we're going to do it. Potential energy due to gravity will convert to kinetic energy. So I'm going to substitute this equation, mg times the quantity, L minus L cosine theta, turns into 1/2 mv squared. The m's will cancel. I'm going to multiply both sides by 2 and then the square root. And we end up with